Okay, should be good. Okay, so let's go to the new set of slides, and finally we are going to talk about quantum algorithms. Okay, and today we'll hopefully introduce three very basic quantum algorithms. Okay, and I guess before we actually introduce the algorithm, we introduce this idea of quantum oracle. Because this algorithm has a weird way of taking inputs, okay? And yeah, they will take inputs in the way which we call the quantum oracle, which is a generalization of a classical oracle. But we are going to see that quantum oracle is different from classical oracle because they do things in parallel, okay? So we kind of think they have this interesting feature that I guess in popular science you also heard about, that is this quantum parallelism. That is because quantum mechanics allows this superposition, so we can kind of allow computation of a function parallelly just by using superposition. But we are going to see that this quantum parallelism is not as easy as it sounds. It's not you just do things in superposition, then you can just exponentially speed up everything. You actually need to carefully control your algorithm. Okay, and yeah, let's get started. So let's get a bit mathematical. We are thinking about evaluating some function, okay, and in this quantum parallelism. So we are going to evaluate this in superposition. So this function, as we mostly consider in this class, we consider Boolean functions. They are kind of the cornerstone of our computer science discussion here. So we have a Boolean function. It takes a discrete input, so just think it's some n qubit for some n, and you output 1 bit. Okay. Yeah. So most of the time the function here is Boolean function. Okay. So suppose we have a Boolean function here, and then we think about how do we compute this function in a quantum superposition. And what we come up with is this quantum oracle UF that compute the UF. Okay, and so what is this quantum oracle or unitary oracle? Do is it takes an input state x and y. Okay, so it's n plus 1 qubit state. So x part is n qubit, and the y part is 1 qubit. So x part will correspond to the input, and the y part will correspond to the output. Okay, and we think what will be a quantum computer way to compute this function is you will map input-output state to another set of input-output state where the input x still stays as x, and the output y become so input x is still stay as x, and you want to compute f of x. Okay, so you use your logic gates to compute f of x, and you write down this y register. Okay, and so this can be done, and we omit the proof here, but I guess you just need to believe me that it can be done. Because you can do this with enough ancilla and the Tavli gates. Okay. But anyway, so this can be done, and this will be our way to quantumly compute our function f of x. Okay, so you take input state x, y. I guess the input state x, y, where x is the input part to f of x, and the y register is where you will write down the output part of your f of x. And after you apply this UF, so the input stays as input x, and the output will become the output register. You will write your f of x in it. Okay, so y become y o plus f of x, and here o plus here because we know this is a 1 bit register or 1 qubit register. So y is on computational basis today 0, 1, and you have this addition modulo 2 or XOR between y and this 1 bit output f of x. Okay, so this is our quantum oracle for function f of x. We think it can compute your function f of x in superposition. because everything can be done in superposition. Okay. And it can be shown that this is unitary. And so here we have some nomenclature. So some names for UF. I think I have called all three of them, but here just to mark it once again. So it's called the oracle or quantum oracle because it's quantum. So it's called the oracle or a query or a black box. Okay. So those are all things that we call this UF that are implementing this function f of x. Sometimes we call it a black box because sometimes we think we don't know what's f, and we only get to access f through this UF box. So it's kind of a box that you don't know how the inside is connected, but you can query the box or query the oracle by feeding some input to it and getting some output from it. Okay, so this is a quantum oracle. And I guess back to the more important part, we want to say this can do superposition. Okay. And so what do we mean compute the f in quantum parallelism or in superposition is that we can feed this x part as some superposition. And so we feed 0 plus 1 over square root 2 to x, and then we will add this f over 0 or f over 1 to the y part. Okay, and here we just later on we will do more interesting on the output state. For now we just say the y as 0 as a empty space to write the output. Okay, so you put 0 plus 1 over square root 2 as the input x and 0 as the input y, then the output state will be this parallel result of computing f of 0 and f of y, because just by the rule we have here. So this 0 plus 1 over square root 2, wait, excuse me, where is, here. Yeah. And so let's just go this a little slower. So the input state can be written as 1 over square root 2, 0 tensor 0 plus 1 over square root 2, 1 tensor 0. And then yeah, and then this 0 tensor 0 part goes through the UF. Then this is the computational basis state, and we know what the UF acts on computational basis state. You will add the function f of 0, so x is 0, so you will add f of 0 on y, and y was 0, so this is just f of 0. Okay, so this 0 0 part becomes 0 f of 0. And this 1 0 part become 1 f of 1. Okay, and so this is what we mean by the quantum oracle compute things in quantum parallelism or in superposition. So you see now you have a superposition of f0 and f1. Okay, so somehow the oracle is able to compute f0 and f1 simultaneously, but I guess that starts saying something negative. And we can think about what so we get this state as output, but can we get both f0 and f1 from this state? And the answer is no. I guess to really say no answer is a bit harder, but we can just try a naive way to see why this is not easy to extract both f0 and f1. Okay. So say after you do this, maybe you put a measurement here, right? You put a measurement on both registers, you measure in computational basis. Then what happens is that this component, this 0f0 component, has amplitude 1 over square root 2, and this 1f1 component has amplitude 1 over square root 2. So if you do measurement, then what you get is that with 1/2 probability, you see the result of 0 f of 0, and with 1/2 probability, you get a result 1 f of 1. Okay, so you see that you just get a probability mixture of f of 0 and f of 1 with 1/2 probability. It's like you pick a random input x here. You just pick a random 0 or 1 as input, and you get a random f of 0, f of 1 as output. Okay. So this is not very interesting, but we will soon see today that there is indeed something you can do faster with this quantum superposition. Although it doesn't, although it don't majorly give you f of 0 and f of 1 with just one application of UF, there is something you can do faster with this UF construction. Okay, and yeah, and here I just want to emphasize a little bit that UF is reversible because every quantum gate is reversible. Okay, and it's also kind of why we want to write UF in this way. Okay. So we have UF times UF just is the inverse of itself. So you have you apply 2UF and you will actually be identity. Okay, so I should write identity instead of 1. Okay, but 2UF is identity because if you apply 2UF on x and y, then obviously the x register stays x, but the y register will get adding 2f of x here. Okay, so y will add f of x and add another f of x, and because everything is binary, so f of x times 2 is just 0. 2 because 2 is 0 in binary, then yeah, so this is y. And you kind of also see here that why our quantum overclock look like this. You have this extra x register so that your function can stay reversible. Okay, you cannot erase all these x otherwise, and and here you cannot just write create f of x out of nowhere because everything needs to stay reversible. Okay, so that's some digression, and I guess before we go to this is a bit weird. Okay, so I guess a little bit more digression is that I want to say this oracle f of x sometimes is a bit confusing because sometimes we think this whole f of x. I guess for now, yeah, it's good to talk about this. Okay, so for now things are a bit confusing because there are kind of two inputs in our description. Okay, that's right. Sorry, that's right here. Two inputs. Okay, so yeah, so sometimes I will mix those up. So hopefully you can discern from context. Okay, so there are two things that we'll call inputs in our oracle discussion. And the first input is the obvious one. That is, we have a function f of x here, and you have an input to this f of x. Okay, and but another input is just this function f of x itself. Okay, because we are going to compute, as you will see in our example very soon, we are going to compute. We are going to think that we don't really know what this f of x is. We just think it's an nb to 1b function, and we want to compute some property on this f of x. And so if you think this whole function as an input, then you are basically need to describe it as the truth table of this whole function. So that will be big N as 2 to n bit string. And here is an example of our big input. Okay. And so, for example, you have a 3-bit function, and it has 8 different values. So this input 0, 1 to 3 has 8 possible value is 0 to 7. Okay, and this f of x, this f function is described by 8 values. So you have f0, f1, f2, f3, f4, f5, f6, f7. Okay. And those values are those values are the 8 different outputs of f of x on 8 different inputs, and they can be arbitrary bits. Okay, and so sometimes we'll think this string is the input to our problem. Okay, the string of the whole truth table of f is our input to problem. Okay, and we don't give it a name, but just so this is, I guess we didn't give it a name, but this is kind of what we think about the function f is. Okay, because the function f can be described by its whole truth table, so the whole big N equal to 2 to n bit string. Okay, and hopefully this clear more things up than create confusion. But back to our quantum parallelism. Okay, So now we have this f of x, and it computes a function compute some function f in superposition, and then want to say this compute function in superposition actually do something nicer. So this is where we get quantum speed up. Okay, and we just see that, or can that we cannot get both f0 and f1 by just having superposition. But there is something you can get is we can get the XOR of f0 and f1 faster than classical computer. Okay, and that brings us to this Dirichlet's algorithm. That's kind of the simplest quantum algorithm that has a quantum speed up. Okay, and the quantum speed up is described in this oracle model. Okay, so as we say, we have some unknown f. We know it's a 1b function, so it's a 1b Boolean function, so it's from 1b01 to 1b01. And this oracle will have a 1b input register and a 1b output register. With the input xy, we will have output x and y all plus f of x. Okay? And now we want to compute f0 plus f1. And classically, I guess you can put proofs here, but it's kind of intuitive. I guess we omit proof here, but it's kind of intuitive that if you want to compute f0 and f1, then you need to learn both f0 and f1. So you need to compute the f1s with input 0 and give f0, then compute the f second time with input being 1 and compute f1 and add them together. That's the most efficient way, classical algorithm you can do to compute f0 or plus f1, and obviously that requires two queries. It means that you need to evaluate f twice, okay? Because you need to compute both f0 and f1 to know what's f0 plus f1, okay? But then we have our quantum speed up is that we have a quantum algorithm that only need to use one quantum or need to place one quantum oracle in circuit to compute f0 plus f1. Okay, so this is really interesting. So it computes neither f0 or f1, but you can compute kind of a global property. You can compute this sum without knowing either one. Okay, and with just one query. Okay, and here is our algorithm. Okay, and so we initialize our both register at 0 and apply headema on the x register and apply x headema on the y register. Then you apply your oracle, then you apply another headema on your first register and the major. Okay, and we can the measurement result will be f0 or plus f1. And you see that we only compute the oracle, the function f1s with this oracle here. And because of this quantum superposition, and the quantum speed up, we can compute this function only once, but then we know the sum of f0 plus f1. Okay, and let's analyze this algorithm and see it actually works. And okay, so we go just analyze what the states are step by step. Okay, so first we say what is psi 1 here. So we start with 0, 0, and then we apply xh on the second qubit and xh on second qubit and h on first qubit. Okay, so first qubit, so now everything still stays in tensor product to each other. So first qubit becomes this plus state, which is 0 plus 1. Okay, and so we see that we are in equal superposition of 0 plus 1 on the first qubit. So kind of like the quantum parallelism example we have here. We have 0 plus 1 over square root 2 as our input. So we are going to compute both f0 and f1 in superposition onto the second qubit. Okay, and the interesting thing here is now we change our second qubit. Okay, and indeed, and actually we change it to something that's not in computational basis. So it starts with 0 state, and we apply x gate, and x gate will flip 0 and 1, so it becomes 1. And we apply another headema, so the second qubit becomes this minus state. Okay? And this is something, another interesting part about quantum oracle is you can also put the second register in some quantum superposition. Although at the first, when we see this, you think this y is kind of a placeholder. You think you're always going to put y as 0 here because y is just some register that you write your function value here. So it's just because quantum gate has no fan out, so you need some register here to write your results. Okay, but we see we immediately see in our first quantum algorithm example that actually this second register being in superposition, in quantum superposition, is also very important because we get our quantum speed up by putting the second register in an interesting state, that is minus state. Okay, and yeah, so at this point our state is plus and minus state, and because of the calculation we are going to do later, we are going to separate this into this form that will be easier to do calculation later. So we separate this plus equal to into 0 plus 1. Okay, so this whole thing is 1 over square root 2 and 0 tensor minus and 1 tensor minus. Okay, and then we see what okay, and then we see then we start to explain why the second register being a minus state is very nice. Okay, and that's when we apply our oracle on this x tensor minus state. So x is some computational basis state, and the minus state is obviously a minus state. Okay, so we think about what happens when we apply this UF on some computational on some input x, but when the output register is this weird superposition of minus state. Okay, and then we break out the minus state. Okay. The minus state is 0 minus 1, and as we indicate here, the UF will write f of x onto the second register. So the second register was 0 minus 1, and after you apply the UF, you add f of x on it, right? Because you have input x, and you will write f of x onto the second register. So it becomes 0 O plus f of x minus 1 O plus f of x. Okay. And now you can just think case by case what happened here when your f of x equal to 0 and 1. Because we have a Boolean function, f of x can only be 0 and 1. And obviously when f of x is 0, then nothing really happened. So the second register will just stay as a minus state. Okay. And then when f of x 1, f of x equal to 1, then something very interesting happened. Okay. So when f of x equal to 1, you will flip the 0 to 1 and 1 to 0. Okay? So the 0 plus 1 become 1 and the 1 plus 1 equal to 0 because we are in binary. Okay, and so 0 become 1 and 1 becomes 0, so you think it is a minus state, but it's not just the minus state because you flip the location of the minus sign. It was 0 minus 1, now it's 1 minus 0, so you get a phase. Okay? And yeah, so you kind of think it's a global phase, but it really isn't. Okay, so this h1 minus 1 phase is very important, as we are going to see very soon. Okay, so when f of x equal to 1, you accumulate a minus 1 in your phase, and so we see that after you apply uf on x, you got these two cases. When f of x equal to 0, you get nothing change. When f of x equal to 1, you get a minus 1 phase. And to write these two cases succinctly, we have this notation. So it's a minus 1 to the f of x, and then you see the whole state is x as always stay as x tensor minus. Okay, so you see you kind of have this quite global phase, we call global phase, but later you see that this is actually a relevant part. Okay. Anyway, so you see you have this h1 phase vector here, and this is minus 1 to the f of x, and I'll just check again that is indeed indeed consistent with the two cases here. So when f of x equals 0, this is minus 1 to the 0, that's just 1, and when f of x equals 1, this is minus 1 to the 1, and this is minus 1. Okay. And this is a very important concept in designing quantum algorithm, and this is called phase kickback. So because obviously you see a phase here, and why we say kickback, because you will because in our original oracle model we will computing we will computing our f of x into this y register. But you see that neither of the register hold the information about f of x anymore, right? This x is just your input x, and the minus state is just minus state. They don't depend on f of x anymore. So the effect of UF is totally contained in this phase now. Okay, and yeah, so this is called phase kickback, and so you kick the f of x information out of the second register by into this kind of global phase. Okay, so this -1 to the f of x phase is now is how you register, how you record the information about f of x now. Okay. And yeah, so with this phase kickback calculation, now we can think about what happens when you apply the oracle on your side 1. So you apply your oracle UF on side 1, which is 0 minus and this 1 minus state. And now you see why we want to write it in this form, because 0 minus is like x tensor minus with x equal to 0, and the 1 minus is like x tensor minus with x equal to 1. Okay, and yeah, so side 2 is you apply UF on this 1 over square root 2 0 minus plus 1 minus, and by our phase kickback notation calculation, this should be -1 to the, so now the information about f here is here, f of 0. So the 0 is this 0, and then you stay 0 and minus. And the 1 minus term get the extra term of -1 to the f of 1, because they equal to 1 here, and the 1 minus. Okay, let's check again. You got -1 to the f of x tensor minus. Okay, and so we got those two things, and now we can, we can clean up these things a little bit. So we take out -1 to the f of 0, so now it's actual global phase vector now. Okay, so you see that those two phase vectors are actually not quite global because they are in different components of this quantum superposition. Okay, so the first part of a superposition has -1 to the f0 phase, and the second one has -1 to f1 phase. Okay, and so even though they are phases, even though they can look kind of like a global phase, but the difference between them actually make a difference to the quantum state. Okay, so you can take our global part, so we take -1 to the f of 0 out of both terms, and then you are left with 0 and minus here, and then you see that you have an extra phase on the 1 minus part. That's the difference between those two phases. So this -1 to the f of 1 minus f of 0. No, this is just a linear algebra. You take out this -1 to the f of 0 factor on both sides. Excuse me. Yeah, and yeah, so you see that the relative phase between the 0 term and the 1 term now depends on this f1 minus f0. Okay, and then we clean up a little bit. Then you see that the whole state is this global phase part that doesn't matter. It's -1 to f0. And the plus state if f1 equal to f0, because if f1 equal to f0, then this -1 to a 0, then you have no phase here, and it's always, everything is always tensor minus, and if this phase doesn't exist, then the first qubit is 0 plus 1, then it's a plus state. And if f1 doesn't equal to f0, then you have 1 here, and then you have 0 minus 1. And yeah, you have 0 minus 1, and I guess you can have -1 or +1 here, but doesn't matter. Okay. And in the end, if f1 doesn't equal to f0, so you have 0 minus 1 here, and the first qubit will be the minus state. Okay, so plus state if f1 equal to f0, and the minus state if f1 doesn't equal to f0. Okay. And finally, you do a Hadamard, and the Hadamard term plus minus equal to 0, 1. So your whole state is basically 0 tensor minus if f1 equal to f0, and 1 if f1 doesn't equal to f0. Okay. And yeah, so so finally you do computational basis measurement on the first qubit. So you see that you get a 0 outcome if f1 equal to f0, and 1 outcome if f1 doesn't equal to f0. And that will exactly tell you what's f1 o plus f0. Because when f1 equal to f0, this means that f1 f of 1 o plus f of 0 will equal to 0. And this is when f of 1 o plus f of 0 will equal to 1. Okay? And yeah, so this is how you get quantum speed up. You can use quantum superposition to compute things kind of coherently. And even though you cannot get both f1 and f0, you can get kind of a global property on your f that you see. You can know whether f1 equal to f0 with just one query to this UF. And this is done by this smart manipulation on the superposition on the first register and the second register. Okay, so that's Dirichlet's algorithm. The idea, I guess the more technical idea is this phase kickback. And yeah, so you kick back the, you put the information about f into this phase, and then you can calculate the difference between the one component and the difference of the phase between the 0 component and 1 component. And then you do a Hadamard to make the 0 component and 1 component interfere with each other again. And yeah, in the end, you can get this 1 bit of information that tells you whether f1 plus f0 equal to 0 or 1. Okay, any question about the derivation of Dirichlet's algorithm? If not, then let's go to, okay, maybe we'll stop early today. Okay, then let's go to our next algorithm. Okay, so I guess let's do a bit of motivation here. So you see that indeed we get quantum speed up here, but it's a very minor quantum speed up. Okay, because here you see the quantum speed up is only, I guess, a factor of 2. So you can compute f0 plus f1 faster, but classical, so you see classical algorithm need 2 query, quantum algorithm only need 1 query. But you kind of feel that the 1 query to 2 query isn't too much difference. It's just 2 constants, a factor of 2. Okay, and so maybe we want to see how big of a difference, how big of a gap can we have between the quantum query can we have between quantum algorithm and the classical algorithm. Okay, and let's stay in the query model because it's easier, and let's see. Yeah, and yeah, so for now we'll stay in the query model and see how quantum algorithm can get faster than classical algorithm. More than this 1 versus 2 difference. Okay, and that brings us to a very similar algorithm, that's Dirichlet's algorithm. Okay, and so now we want to get a bigger separation, and we start using bigger function. Okay, so our function is now actually n bit input to 1 bit output. For Dirichlet's algorithm, the input was only 1 bit. Okay, and this is kind of like a very brute force generalization of Dirichlet's algorithm and the Dirichlet's problem, as we will see. And anyway, so the problem is set up this way. So you have a function f of n is n bit to 1 bit, and now we have a new concept. I guess this should really be I think I guess it's okay, but it should be highlighted a little bit. So we have this concept of promise that our function is not arbitrary function. Okay, so function is still unknown to us because it's kind of the input, but we have some promise on a function that is not arbitrary n-bit Boolean function. Okay, so we promise that our function is either a constant function, that is the function is either a constant function or a balanced function. And by constant function, we mean that the output is a constant. So constant function means that the output is always 0 or always 1. Okay, so whatever input you put, if it's a constant function, then I guess there are only 2 constant functions. So first constant function is this function always output 0, and the second constant function is this function always output 1. Okay, and so that's constant function. And a balanced function means that the function, okay, so this function has 2 to n different input, and that will correspond to 2 to n different output. And we mean that the number of outputs being number of so the 2 to n different input will go to either 0 or 1, right? Because it's a Boolean function. And then it means that half of them will map to 0 and half of them will map to 1. That means it's a balanced function. Okay, so that means I guess I should say inputs. Okay, so the number of inputs that map to 0 should equal to the number of inputs that map to 1. That's a balanced function. So 2 to n over 2 of them will map to 0, and 2 to n over 2 of them map to 1. Okay. So any question about the definition of George-Jozsa problem? Oh, I guess this is just a promise of function. I haven't said problem. But the problem is that so your function is promised to be in one of those two very specific forms, and you are going to decide whether it's a constant function or a balanced function. Okay, so decision here is also just one bit decision. It's either this answer or this answer. Okay. Any questions so far? Do people understand the question? So we are going to take unknown function here. It's some 2 to n bit input to 1 bit output function, and it's promised to be all the output being 0 or output being 1, or half of the output. I guess I should stay with output, or half of the output is 0 and half of the output is 1. Okay. And then we want to decide whether it is a constant function or a balanced function. Okay. And okay, so let's get back to our query complexities. Okay. And so we want to show that this problem has a better separation between classical and quantum. And so first we need to think about what is the number of classical queries needed to solve the problem. And this one is a bit tricky. So it depends on what you think about is a classical algorithm. Okay. And also how much requirement you put on classical algorithm. Okay, and so if you are in the most strict model, we want to have our classical algorithm being deterministic. So so we want the classical algorithm to solve this problem with no error. Then we see that we need to basically use exponential in smaller number of queries. Okay, we need to query 2 to n minus 1 plus 1 queries. Okay. I guess this is not rigorous. This is not let me highlight this first. Okay, so this is not a rigorous derivation, but just think about what the classical algorithm will do. Okay, so you want to see whether your function is balanced or constant, and basically what you'll do is you are just going to feed different input and look at the output. Okay, and so when it's a constant function, and you will always see the same output. It's going to be output always being 0 or output always being 1. And when it's a balanced function, then sometimes it will be 0, sometimes it will be 1. Okay, and but if you want to have no error, that means that I guess so the most obvious function, the most intuitive classical algorithm to do this is you just keep querying f and just see what's the output. So you just ask what's f of 0, f of 1, f of 2, etc. Okay, and if they are all the same, then you see it's a constant function, and you see difference, and you see difference. Then you say it's a balanced function. Okay, and so if you want to make no error, so you see a difference, you say a better function, and then you see no difference, and so you see no difference for some time. For a really long time, you say it's a constant function. Okay, and now the question is how long you need to wait here to make sure you don't make an error. And that means that if you have a balanced function, how many number you need to see to make sure that you don't mistake it as a constant function. And that is you need to see at least half plus 1, because if you are really unlucky, you can query your balanced function with a lot of query and see the half number of the 0 here. You can see a lot of 0 here because half of them are 0, and you think it's a constant function, but it's actually a balanced function. You just keep seeing all the 0 here, for example. Okay, and so you want to make no mistake, you need at least 2 half plus 1 queries here. Okay, and I guess it's time. Oh no, sorry. Yeah, let's keep going. And yeah, so you need at least half plus 1 queries to make sure that your classical algorithm doesn't make a mistake. Because when you have balanced input, you need to see half plus 1 to make sure it's actually a balanced input. Not that you are having balanced input and seeing half of 0, and you see a lot of 0 thinking it's a constant function. Okay, and but if you allow randomness in your algorithm and allow some mistake, so say you only want like a 2/3 probability of success, then it's kind of easy to see that you only need a constant number of queries to make this. So basically, you just put instead of this 0, 1, 2, 3, you put random. you have random x. Okay, you have f of x1, f of x2, and where xi are random. I guess I should write second page. Okay, so if you have a random algorithm, then you can have x1, x2, xi, id random, and then you ask what's f of x1, f of x2, f of xi. Okay, and when you see a difference, you see it's a balanced function. Okay, and and in this case, you see that if you have a balanced function, then each subsequent query, this random query, is about 1/2 probability to show different output than the previous result. Okay, and so the probability that you have a balanced input and that your random queries having all the same output decay exponentially. Okay, and so with some probability theory, you can see that with only probably 4 to 5 queries, you can get a very good probability that when you have a balanced input, you actually see that it's a balanced input. And obviously, when you have a constant input, you query this random location, you will always get a constant output. Okay, and so randomized algorithm can solve this really quickly. But for the sake of saying that we have a big classical separation, we consider this model where we want to solve with no error. Okay. Okay. If we want to have a deterministic algorithm that solves with no error, we need this exponential number query 2 to n minus 1. Okay. And okay, so that's classical query complexity. It's a pretty complicated. Depends on whether you want deterministic algorithm or randomized algorithm with constant success probability. But the quantum algorithm is very good. So quantum algorithm actually only need one query and give a deterministic outcome. So in this sense, it's very comparable to our case here, because the quantum algorithm actually also has no error. And once again, you only need one query. I guess I should write it somewhere. So the George-Childs algorithm only uses one query, and it's very similar to the George algorithm. So you see, you still have the Hedema and Hedema, the whole bunch of Hedema structure, and this one is just 0 on X. Okay. So everything is the same except that the input register is now n qubit, and instead of just one Hedema here, you put n Hedema here and here. Okay. So this is George-Childs algorithm, and let's see. Can we? I guess we be sure on time, so we'll talk about calculate. Okay, and so let's talk about the easy part of the algorithm. And the easy part is the first few steps. Okay, and so the input is so the input to the oracle is side 1. And side 1 you have Hedema on the second qubit, so just as before we are going to do phase kickback, and so we have the minus state on the second qubit. And the first qubit is a bit more complicated. You had Hedema to the n on 0 to the n, so we have all 0 input state, and put a Hedema on every qubit. Okay, and then because it's a tensor of operator on tensor of states, so you know it's just the tensors of the output state, and you know Hedema 0 is plus state, so you just have n plus state tensor together, and let's move all their coefficient part. So each one of them has a 1 over square root 2, and there are n of them, so you have 1 over square root 2 to the n. And then the actual state part, you have a 0 plus 1, tensor 0 plus 1, tensor 0 plus 1, n times. Okay. Okay, so this is kind of complicated, but if we are smart enough, then we can find a very very clean notation for this. We found out that this is just a summation of all string of 0, 1 to the n, all possible n bit string, because in each bit or each qubit here, you have the possibility of choosing being 0 and 1. And so when you multiply all this n 0 plus 1, then you get a result of all possible strings. And so yeah, so there are n n terms with 2 terms inside multiplying together, so there are totally 2 to n terms here, and that exactly matches that there are 2 to n different strings here. Okay. So yeah, so we just write this as a summation over x being all possible n bit string and x here. And yeah, so for example, the 0, tensor 0, tensor 0, 0, 0, tensor 0 component will correspond to the all 0 string here. Okay. Yeah, so that's the input to the oracle. And you see that this is kind of like in George algorithm is uniform superposition of all possible computational basis state. Right? So X are computational basis state. Computational basis state of m qubit are labeled by these strings, and this is just a superposition of all those X with the same amplitude. Okay? So this is a uniform superposition of all possible inputs here. And then on the second register, you have the minus state. And I guess we have 1 more minute, so let's finish this part. And then just as before, we have phase kickback. Okay. I guess we derive phase kickback. I guess we are being a little lazy here because we derive phase kickback with the 1-bit function. But you can easily verify that the phase kickback derivation works even if your x is n bit. So that's so this is phase kickback. Phase kickback. Okay. So this works even if x is n bit string, and so you can easily write down the state after you apply the oracle. Okay, so that is you have this summation over OX and minus, and by phase kickback you just get -1 to the f of x in front of every x here. Okay, and then I think it's time for a break now, so I'll stop here, let you study this, and we'll continue our analysis of Dirichlet's algorithm on next class. Okay, any question? Let's take a 10-minute break.这是我新写的那篇吗？我的要真的 nice 那篇，他们好，对。因为他们的那是就是他就最重要就是对是他的报告，好做报告，那他因为他的。那
不，你想入职，就你们想去哪里？
就是重复你说最后一次跑的结果吗？最后一次跑的结果可能会不太一样，但是它上面会不一样，就它的 history 历史会不一样。
就有可能最后是跑那种，这个好分。
要看你说的101什么？你是说只有这一段会领先的结果吗？上面可能不一样啊，可能他们在上面有跑出不同的结果，然后但是要看你的101什么意思啊？101是照他的我有点忘了，他这个东西有点奇怪。S 是因为它有一个全部的 history， 它有一个所有的 history 串起来的，跟有一个只有这一段的结果的。就是我先因为我忘记上东西，我先写下我想法。假设我每次都是做一个 piece 嘛，所以这里会有一个01，然后这里会有一个01，这里会有一个01这样子，其实就是历史人学跟这个所以有的全部的 history 会是这个是0001，然后这个是001这种感觉，这样子。但是它的那个 S 的东西，我看一下就是它 S 不知道是这里的01还是全部的00。看起来是只有那一段的，就是只有那次很差的结果这样。
那他的那个
看他有他说什么，他自己是比较全部的串起来的结果。这个 I 是什么？差不多，对他做的差不多的事情。它看起来是最下面那层的 distribution 吧，就是你就走下来每个都有几率嘛，然后这里会有 distribution 这样子。
走到什么？
对啊，走到最底下的 distribution。好像，那你有看到，我就看迪卡的吗？我就觉得好像迪卡都没有看过给别人看第一。
然后第一套它最上面有一个，还是我后来有看过一些，但就不知道怎么看，我自己想要用，
我有点习惯了。懂。我自己看有没有看到，因为我没有看过它。没有。快要。我今天晚上。我看一下。好像时间差不多。让我下课来问他。
Hello. Yeah. Let's go back to George algorithm. So as we said, once again we use face kickback here, and although we didn't do the whole proof, I guess we can flip back to face kickback here. Okay, so you see that here, if you just think of this x as NB string, then this derivation of face kickback just work out when x is n bit, right? Here we didn't use x is a 1-bit state at all. We just use this minus is a 1-bit state, and that's true for George setup. Okay, so x can be an NB string, and then face kickback will still give you the same result. It says that you have x tensor minus, then after you apply the oracle, it gives you minus 1 to the f of x times the x tensor minus. And let's jump to back to our George Dosa. Okay, so we have face kickback, and we have this superposition of x, uniform superposition of x as input and minus as the output. So we have this output, then after apply the oracle, we got the HR minus 1 to the f of x our state. So we have sum over. So we still sum over all possible input, but each input has a different minus 1 to the f of x based on it. Okay. So yeah, so we have this weird superposition of different input and attached by different faces. Okay. And now we go to the hardest part to analyze part of the algorithm. That is, you apply headma on the input register. Okay, you apply headma onto the n on the input register. So you have these weird faces, and you try to have them interfere with each other. So you apply headma. Okay. And so really what you need to do is you need to calculate what's headma to the n on some arbitrary computational basis at x. Okay, and actually we have a very clean formula to describe this thing too. Okay, even though you think this is complicated, so x is a string of 0 and 1, so you're going to tensor a whole bunch of plus and minus together. So how do you write this cleanly is, well, we go kind of one by one, step by step. So we think first we think about what's headma on 0. Okay. So on 1 qubit, okay. So headma on 1 qubit is, well, we know headma on 0 is plus state, that's 0 plus 1, and headma on 1 is a minus state, that's 0 minus 1. And so that's nice, but actually we can write those two things in a very clean algebraic notation. That is, you headma on x, then is always 1 over square root 2. And 0 plus 1, summation over 0 and 1, but with different faces here. Okay, and the different face is minus 1 to the x multiplied by z. Okay, and what do we mean? That means that out of those four possibilities here, you only have a minus 1 here. Okay, you only see a minus 1 here between these one state. So you see that between your input 0, 1 and output 0, 1 pair, only when both input is 1, output is 1, you get a minus 1 phase. Okay, and so to express these things only happen when both of them are 1, you put the product of input up here. So you have x star z here. So this thing is 1 only if both x and z is 1, and it's 0 otherwise. Okay, and so you get this h1 minus 1 phase only when both x and z are 1, and that will match this x0 equal to 0 plus 1 and x1 equal to 0 minus 1 into knowledge we have here. Okay, and so we have this kind of more complicated but actually more usable notation here of h of x equal to 1 over square root 2 summation z minus 1 to the x star z, and so once again, I guess just as a notice, so z here is a dummy variable, so this something summed over is 0 or 1, and yeah. So you're summing all possible computational basis state as you have here, and with different phase -1x dot z. Okay, so that's 1 qubit, and with this formula for 1 qubit, then you can think about formula for many qubit. So you have Hadamard to the n on n different qubit x1 to xn. Okay, and obviously this is a tensor product, and this is a tensor product, so you can just apply the formula separately on each of the n qubits. So on the first qubit, you have the 1 over square root 2 summation z1 -1 to the x1 dot z1, and on the second qubit you have the summation z2 and x2 dot z2 here, and here we're regrouping together all the 1 over square root n, there are n of them, so it's 1 over square root 2 to the n. Okay, and so this is our result, but this is still ugly. We want to clean this up, so we put everything inside the summation. So we put all the summation. So you now have summation z1 to zn, and we will meet the equal to 0, 1 part because it's a bit too long. Okay. So you have summation z1 to zn, you know they are all belonging in 0, 1. And now we group all the phases together. You have -1 to the x1 dot z1, and -1 to the x2 dot z2, -1 to the x2 n dot z, all the way to -1 x1 xn dot zn. And we know you multiply two phases, then I guess you multiply two exponentials, you just add the exponent together. Okay, so all the -1 together is -1 to the x1 dot z1 plus x2 dot z2 all the way to xn dot zn. And then you left with the actual quantum state part. It's just a tensor product of all those states. So it's just tensor product of z1, z2 all the way to zn. Okay, and so now this is a nicer form, and we can invent a notation, this bitwise inner product, to write this x1 dot z1, x2 dot z2 all the way to the xn dot zn, because we can think the input string x, so this x here, x is nb string, so we can think this nb string as basically n-dimensional vector. Okay, and similarly we think this is z, so this is x we think is an nb string, and then we can also think this as an n-dimensional vector. And similarly, we think this z1 to zn as an n-dimensional vector, and then we can take the inner product between those two vectors. Okay, so x as an n-dimensional vector, z as an n-dimensional vector, z1 to zn as an n-dimensional vector, and then we take the inner product. This will be this x1 dot z1 plus x2 dot z2 over to xn dot zn. This is a bitwise inner product between those strings, and yeah, we call this bitwise inner product because this is like an inner product between n-dimensional vectors. Okay, and so this vector is just -1 to the x dot z, and then we have that this z1 to zn. We just call it as a string z, and then the summation of every bit between 0 and 1 just means that your summation is z being all possible 0, 1 bit string. This is kind of like what happened when we do the first Hadamard. Okay. Yeah. So any question about this derivation? So this result is kind of important. It's nicer to memorize this. Okay. So you have h1 to the h to the n computational basis x. The result is the superposition of all possible computational bases with the different phases, and the different phase is -1 to the input inner product with output. So input x, inner product with output z. And yeah, so it's a bit of overload of notation here. So here this inner product is bitwise inner product, and this is multiplication. I guess multiplication for one dimensional vector is just inner product is equal to inner product. Sorry, I guess the inner product for one dimensional vector equal to multiplication. Okay, so the notation is kind of consistent. And yeah, so anyway, we have Hadamard to the nx as this closed form expression, and finally we can finish our calculation on side 3. So remember our side 3 was this 1 over square root to the n summation over all possible x and minus with this h of x minus 1 to f of x and Hadamard to n on your x register. Okay. and yeah, and then we just calculate this kinematic ln x, and so we put it here. Is another 1 over square root 2 to the n, and the summation of all computational bases. Now you change the name to summation z to all possible nb string z, and then -1 to the x dot dz. Okay. And now we group things together. We kind of change the order of summation. That's something we want to do a lot. So we sum over z, and now we group everything with x together. Okay. So everything with x, you have the summation x, and -1 to the f of x times -1 to the x dot z. So you have -1 to the x dot z plus f of x. And for reasons, we also put these two amplitudes together. So it's 1 over 2 to the n here. Okay. So and then we left with the actual state. That's the tensor minus. Okay. And so you see that this is a sum over all computational basis state z with weird amplitude. This is a function of z because x gets summation over and tensor minus state. So the second register will just say minus state, doesn't really matter. So now we just want to see what's the distribution of first register. It has this really weird function. It's well, all possible z, but with different amplitudes. This is the summation x -1 to the x dot z plus f of x over 2 to the n. Okay, and okay, so that's the output state before measurement, and we really want to know what this is because we are just going to do computational basis measurement. So we want to know what's this number for different z, and it seems complicated, but we are actually already done here because they are actually very concentrated on the constant case. Okay, so the only one, so this complicated function, the only one we care about is what is the value of this function when z equal to all zero string. Okay, and excuse me, and when z equal to all zero string, then this function is very easy to calculate because you can get rid of this inner product part. Because you have an x inner product with all zero string, it's just going to be 0. So now this doesn't depend on x anymore, so you have summation x. Oh, sorry, I guess it still depends on x, but you don't have this inner product part, so now you have summation x, just this function part, -1 to the f of x over 2 to the n. And now you know when you have a constant function, so f of x equal to 0 to 1. Then you just have -1 over 2 to the n and sum over 2 to the n times. And so when your input is a constant, so f of x equal to 0 to 1, then you know this number is either 1 or -1, depends. So if it's 0, then you are summing over a lot of 1s here. And if it's f of x equal to 1, you're summing over a lot of -1 here. And either way, the amplitude square is going to be 1, so the probability of actually measuring the all zero string is actually 1. Okay, so you see that when your function is constant, the probability of measuring the all zero string is 1. And when you have a balanced string, then this probability is actually 0. Okay, so when it's a balanced string, then you see that I guess I should really write this here. So when f of x is equal to 0, then you have -1 to the 0 equal to 1. And f of x equal to 1, then -1 to the 1 equal to -1. Okay? And so when you have so when you have a balanced input, I guess the balanced the balanced function, then the number of 1 here and the number of -1 here will be the same because it's balanced. And so when you do a summation, the 1s and the -1 will cancel each other. So the amplitude will actually be 0. So you have probability 0 of getting the all 0 output. Okay. And other outputs, you can be a complicated function, but we only need to know that on balanced input there is no other output. There is balanced input, then you only get other output. You never get all zero output. Okay, and so here we see what our algorithm should do. So we say that at the measurement here, when you see all zero output, you know it's a constant function, and if you measure anything else, then you know it's a balanced function. And this is the algorithm that's making no error. You have 100% probability of getting correct. Okay, and that's in contrast to the classical situation where you want to make no error. You need at least 2 to the n different t to the n minus 1 queries. Okay, any question? No. Yeah, and so I guess a bit of a recap. So yeah, so here we use kind of 2 techniques. So once again, we use our fast kickback technique, and and also we have this I guess calculation tool here. We have this closed form expression of head map to the n on x that give you 1 over 2 to the n. 1 over square root 2 to the n, summation over all possible z, minus 1 to the x dot x inner product with z, and this zk. Okay, and yeah, we see you have this really interesting excuse me, interference result that when you have constant input, the output will be always this all zero string, and when you have balanced input, balanced function, then the output will never be this all zero string. Okay, any question? If not, then let's talk about the next algorithm I want to talk about today. Okay, and I guess the motivation here is that so in Dirichlet's algorithm, we see kind of an exponential speed up between quantum and classical no-error algorithm, but we see that we already say here, if we allow randomized algorithm, then it's still very easy to solve this problem, right? As we say, the balance and the constant balance function are really easy to distinguish if you are allowing some randomness and some error. You just random sample, and very soon you will tell whether the function is constant or balanced. You just sample random inputs. Okay, and so now we want the separation between quantum and the classical algorithm for random inputs, and that give us this Bernstein-Marzoroni algorithm. Okay, and I guess before we say the algorithm, we should say the problem. Okay. So once again, this is a promise problem. So we have n-bit Boolean function, and we now we have this really mathematical promise. We say that we promise that there is some secret s such that f of x equal to s dot x. Okay, so s is another input string, and this dot here means the inner product, bitwise inner product we said before. So you have s1 plus x2. Oh, it's hard to pronounce. So it's s1 plus x1 plus, sorry, maybe right. s1 times x1. This is s1 times x1 plus s2 times x2 plus da 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 all the way to sn times xn. Okay, and yeah, so the output has this really particular form. Okay, so every function, so the function is basically indexed by this s value is s-bit, this n-bit s string, and the problem is just find this secret string s. Okay, so you got the function, it's encoded by the secret string s, and the problem you try to solve, now this is not a decision problem anymore, you try to find the value s here. Okay, it's a bit different. Okay, so it still has this Boolean function as input, but you are trying to find some secret about the Boolean function, which is a bit string. Okay, people okay with the problem? And as usual, let's talk about the classical complexity first. And there's a very simple classical algorithm to find this. That is, you can just query a different input to get the whole string. That is, you query the string that's kind of like the indicator function, I guess. So you put the input x like in this form. So you see that if you have x as 1000, then the inner product between s and x will just be s1, right? Because x1 equal to 1 and x2 to xn are all equal to 0. So the inner product is just s1. Okay? So if you have f of 10000, then the output will be s1. And so just similarly, if you put the input as 010000, you get x2. Okay? And obviously you repeat this for all possible different inputs here, and you get s1, s2 to sn, and so you will learn just the whole string s. So you see that the classical method can there's a classical algorithm that will learn this s we using n queries. Okay, and then by some information theory argument, you can also you can very easy to show that you also need n queries to learn s. And I guess the argument is that there are 2 to n different. Yeah, the argument here is that there are 2 to n different s here, and so you need or I guess the other way to say this is s is an n-bit string. So there are n bits of information here. And every time you query f classically, you just get a 1 bit output. You get a 0, 1. And so if you want to learn the n-bit string, then you need to have n-bit information. So that means that you need to query fn times. You need to query fn times classically to learn the string s. Okay, and that's true even with randomized algorithm. Okay. So that's kind of our goal here. So we want that some problem that even with randomized algorithm you cannot do very fast. Okay, and that's the bursting running problem. Okay, so in bursting running problem, classical algorithm always need n queries to solve it. Okay, and then let's see about the quantum algorithm. Okay. So quantum algorithm can actually solve this with 1 query. And even funnier, the algorithm is the same as the George-Jozsa algorithm. Okay? So you see this is the same George-Jozsa algorithms. You put the quantum oracle inside, and you put the minus state on the second register to do phase keyback, and then just headmark the input to create the equal superposition of everything. Then you headmark it again and measure. Okay? And so this is really funny. As we say, I guess one interesting point before we do calculation is that remember we say S is an n-bit string, right? And we say classical algorithm, classical query can only get 1 bit output each time. And but here we only put 1 query in this quantum algorithm. So we see that actually one quantum query can create n bit output, n bit of information. Okay, that's because that's really funny because you create something because you have an n bit on the input register. So you can actually read out n bit of information from the input register, even though you kind of think the input stay as the same. But if you think about the algorithm we have done today, we always doing measurement on the input register. Okay, so that's kind of an interesting point of the quantum algorithm. That is, you do superposition on, you put the equal superposition on the input, and you you do this phase keyback. You get different phases on them, and you do this interference on the inputs, and then you can actually read information about your function from the input register. And you can read even more than 1 bit of information from this input register because it has n bit. Okay, And so that's some advertising for bursting of the running algorithm. And I guess let's go back to the calculation. And the calculation, as we say, well, it's the algorithm is the same for, I guess the quantum part of the algorithm is the same as the theoretical sum. So let's just skip to the size 3. And as it says, size 3 is summation z, and summation x with this weird part. So 1 minus 1 to the x dot x inner product with z f of, plus f of x over 2 to the n, and with the state being z on first register, tensor minus z on second register. Okay, so it's equal superposition of all computational basis state on the first register with this weird amplitude summation x minus 1 to x dot z plus f of x over 2 to the n. And okay, and what's different now is the promise on f of x. Okay, so in the previous problem, f of x is either balanced or constant. And but now we know f of x has this very close form expression. F of x is just s inner product with x s. So let's just write it here. F of x equal to x inner product with s. And now we can do more calculation. And so we just look at the exponent part here. We have x inner product with z plus x inner product with s. And we know inner product is linear, or you have a distributed distribution law on inner product. So this is, you can group together this z and s. So you have z plus s inner product with x. Okay, and I guess doesn't really matter, but I have O plus here. You can also have a regular plus here. Okay, so z plus s inner product with x. Okay, yeah. So that's the calculation we have running. Okay, and now we analyze what's this thing, and we find out that this thing is actually equal to 1 if only if z equal to s. And the proof is we do analyze here. Okay, so what happens when z equal to s? When z equal to s, then oh, I guess that's why I put O plus here. Okay, sorry. So when z equal to s, then z O plus s equal to 0, or 0 string, because yeah, basically because 2 equal to 0 when you mod 2. Okay. When z equal to s, this is z O plus s is 2z mod 2, and it's just a O0 string. And then you have O0 string inner product with x, and that will just be 0 all the time. Okay, and so when z equal to s, you just have 1 over 2 to n sum the 2 to the n time, and that equal to 1. Okay, so you know this whole value here, this whole parenthesis, that's what we concern. The whole parenthesis equal to 1 when z equal to s, and then when z not equal to s, you can show that equal to 0. Okay, so you can do this in 2 ways. First is you can do careful proof that this will always be a case. Okay, it's always equal to 0. And you can also treat it a little bit by knowing that size 3 is a normalized state, and so if one component has amplitude 1, that is the s component has amplitude 1, then all other components must have amplitude 0, otherwise the size 3 will not be normalized, because the amplitude square should sound equal to 1, and this is already taking all the weight there. Okay, and yeah, so in the end we know this thing is just s. Okay, because this factor is 1 if only if z equal to s, so you only have s here. Okay, and since you got s here, you just measure the first register and you get your NB string s. Okay, and then as we said, quantum algorithm. So as we show, quantum algorithm only need one query to learn s, but classical algorithm need omega query, even with randomized algorithm. Okay, so we have this. Okay, so this seems like a smaller separation is 1/n compared to the. So in George-Josa we had 1/2 to the n/2 plus 1. So this seems like exponential separation, but this is assuming you have no randomness in classical algorithm. Okay. Okay. And but in bursting about the running algorithm, we have this 1/n separation, but it allows the classical algorithm to use randomization. And so I guess for the next time, we are trying to have a base of 2 word. We are trying to see. So natural question is, can you have exponential separation? Means something to 2 to n, and between quantum algorithm and randomized classical algorithm. Okay, and that will be Simon's algorithm. I guess that's right here, Simon's algorithm. Is I guess it's Polian, if I recall correctly. Polian versus 2 to n, order 2 to n. Now kiss me. Actually, I guess it's kind of 2 to the order n, 2 to the order n. Between quantum and randomized classical. Okay, that's next time. And I guess question for now, or we have a bit of extra after this slide. Okay. Any question about bursting about the running algorithm? It's really, I guess not the same algorithm. It has the same quantum circuit as the George-Josa algorithm, but you have different classical analysis after you do measurement. In George-Josa, the classical analysis is you see whether your output string is all 0, and in bursting about running, you want to see where the output is, the measured output is your secret string S. Okay. Okay, and as we say, we will talk about Simon's algorithm next time, but now we want to say a bit of high-level generalization about quantum query complexity. Okay, and so this is some kind of high-level formalization of quantum queries. Okay, and remember in quantum query, I guess in quantum query complexity in general. We have our input. We are trying to probing things about Boolean functions. Okay. I guess in Simon's algorithm we are going to have a function that's not Boolean, but for now let's think about Boolean function. But anyway, so we have functions f of x equal to 0, 1 to the n to 0, 1, and then we think this whole function is the input, and they correspond to. So this whole function will be described by its truth table as a string of big N equal to 2 to n bits, and we think we do a query is kind of like a look at the location of. Okay, so sorry, here I should type. It's kind of a look at the location of these different boxes, and let's change the numbering. So I guess it's easier if I put a box here. So we start from f over 0 to f over 2 to the minus 1. Okay, and yeah, and so we think f of x kind of like a string of black box from f over 0 to f over 2 to the minus 1. And when you do a classical query, you kind of look at location, and you do quantum query, you kind of having this weird superposition of you look at different position in superposition. But anyway, query complexity means that you have this f and you have this interesting uf. So you have this uf, and you think about how many uf you need to put in your circuit to compute something about f, and something about f is really what your problem is asking. So for example, in Dirichlet logarithm, you want to compute f0 plus f1. Okay, so that's quantum Curry complexity. You have some problem about this unknown function f, and you want to see how many of these queries oracles you input in your algorithm to compute it. And here is a schematic of quantum query algorithm. So we think a quantum algorithm kind of always act like this. Oh, I guess I forgot to put the input there. And since the input is actually inside this UF, so the input state to the algorithm is you can just put a 0 on the start, and then you apply some unitary that doesn't depend on f. So I guess I should say. So the algorithm will consist of a whole bunch of unitary. I guess they are described by those u1, u0, u1 dot ut. They are independent of your function f. Okay, they don't know about your f. So the quantum algorithm in general, you will start with O0, and you rotate this O0 state with some unitary that depend on f, arbitrary unitary, and to something you want. Then you apply your query, and you can apply another unitary, then you can apply another unitary, etc. all the way. And so you will do this in t times, some big t times, and that means you place the big T different UF in your circuit, and in the end you can do another UT, and you do measurement on some part of the circuit, measurement here, and then you get your result. Okay, so that's your quantum circuit. Yeah, so you get a result out of your measurement. Okay, so that's what do you do when you run a quantum circuit, and we're seeing we have 3 very simple quantum circuits. Sorry, quantum query circuit that only have one UF and only one query, and so we just have some U0 and UF and some U1, and then we just do measurement and get the outcome. But we have a more complicated algorithm. We will do this thing. It's an interleaving between unitaries that doesn't depend on your function, and your oracle that tells you some information about your function. And you want to learn some information about this small f using as little UF as possible. Okay. And yeah, so quantum current complexity equal to number of layers equal to this big T here. Okay. And I guess this is kind of a weird model of saying computation, because when we think about circuit model, we start with saying we have input here and we have output here, and we want to have a short circuit that compute from input to output using as little gates as possible. Okay, and why do we switch to this weird quantum query model where we have an input kind of encoded in this UF, and we want to compute things about UF with as little UF as possible? The first reason is kind of a funny reason. That's that because time complexity is really hard to compute, so we study query complexity instead. Yeah, because you can kind of feel that query complexity has this very information theoretical feature that you know really nothing about f, and so you are trying to learn something about this f, and if you don't have enough information, it's impossible to give an answer. So for example, here we can, in Bersin Varani, we can have this very information theoretical argument saying that there are n-bit unknowns in your f that you are trying to learn, and if you don't query n times, you just cannot learn it. Okay, so query complexity makes it so in this query model it's much easier than time complexity to having a concrete lower bound. Okay, it's much easier to calculate concrete query complexity, and okay, so it's easier to compute, but also one is something useful. And then here we get a bit hand wavy, but in a lot of problem, actually the query complexity is a good approximation. We just say it's a good estimate of the problem's hardness, and will approximate the time complexity. And obviously this is not usually true, so alternate conditions apply. Okay, and anyway, so that's a query complexity model, and a lot of things we do will be query complexity model. And another summarizing thing I want to say here is the first version of quantum oracle. Okay, and this is something you already do today. That is, you can do phase key back. Basically, this is kind of a more formal way to say phase key back. That is, instead of is picture. So we define quantum oracle as this. This is kind of a standard version of quantum oracle. You have input register, output register, and you write f of x on your output register. And however, things that you can do phase key back to make a quantum oracle equal to this phase version. And basically, you have some UF tilde that apply on some state x, and you get -1 to the f of x. Okay, and so that's the first version of the oracle we talk about. But here we make a bit more complicated version of the first version. We say we can also put a control on a control register on the first version of oracle that's made up for this white register here. So you are not losing a register. So you can put a control register here, such that if control register is 1, then you put a HR phase on your state, and the control register is 0, then you don't put the HR phase. Okay. So yeah, and I think you will prove in your homework that the phase version of oracle can be controlled from the standard version of oracle, and actually you are going to show that they are equivalent. So you can control phase version of oracle by having one query to the standard version, and so I guess that's right here. So in the homework, you are actually going to show that you can control the one UF tilde from one UF, and also you can control one UF from one UF tilde. Okay, they are equivalent to each other in terms of number of query you put in your algorithm. Okay, any question? And yeah, then I guess we have something very small to say here. Okay, and yeah, so some comparison between classical oracle and the quantum oracle. I guess people, I'm not sure how many of you actually learn about classical oracle, but let's just say here. So I guess I don't really need a slide. Let's do this. Okay. So classical and quantum query. So quantum query. I guess that's back to the standard version. Is these blocks. Okay. So it has x part and y part. Okay. And x is the input, and it will write f of x to the output register here. And classical oracle really don't need two register. You just have x as input, and you will compute f of x. And I guess in this slide, it's just a comparison between classical oracle and the quantum oracle. And I also want to say that why don't you have a quantum oracle just kind of do this, okay? And here I want to argue that why can you do this? It's because first of all, this can be non-reversible. Okay, so say you have a constant function, you will map all x to 0, and that's just another unitary operation that's not reversible. Okay, so you want your quantum oracle to be this to have a register that keeps the input x here, keep the information about input, and also having yeah. So because the quantum gate must be unitary and means reversible, so you must keep the information about the input, so you can always reverse it, even if your f has very low information. And also you cannot just okay. So I guess it is kind of a straw man. So you can also not just have x and x f of x like this. And this is also not allowed because you cannot just create the extra register. Quantum operation must, the number of lines must be consistent. So you must have some line here, and that's why you put a y here and add your f of x on your y. Okay, so this is necessary. Okay, try to explain a little bit why quantum oracle look like this. So the classical oracle is maybe more intuitive. You put x inside, you get f of x outside. But for quantum oracle, you want it reversible, so you need to have x here. So I guess maybe I should draw this line. It's okay. Yeah. So because it's reversible, so you need to keep this x output, and you need to have one input line here. Okay. And finally, my last slide of rambling is that it's very easy to show that the power of one quantum oracle is more than the power of one classical oracle. So basically, if you want to compute f of x from this thing, you just put x here and put a 0 here, and you will compute f of x. Okay. So one quantum oracle is always better or equal to one classical oracle. But the big question in quantum complexity theory study is how much better is a quantum oracle than classical oracle. So basically, we are looking for quantum speedup over query algorithms. Okay, so we want to see what's the largest possible gap between quantum recurrent complexity and classical query complexity, and I guess I can actually put more things here. And also, when is there a gap? Okay, so when will there be a gap? When will there be a gap? So how do you create a quantum speedup? How do you create a gap between quantum query complexity and classical query complexity? So basically, this is we are trying to study quantum speedup. Okay. If you have a better quantum query complexity than classical query complexity, then you think we have a quantum speedup. So we are studying quantum speedup in the bigger scheme of things. Okay. If no question, then I think we are almost in time. So we can stop here and stop 3 minutes earlier, and see you on next Tuesday. Okay. Yeah. See you. Oh，等一下。